Hey guys, so in this video we're going to talk about the gas laws. So there's a few of these. We're going to talk about what they mean, how you do math with them, and all kinds of stuff. So before we get into these gas laws that I've been talking about, we need to talk about something called standard temperature and pressure. So there are just these temperatures and pressures that scientists have decided are standard. We use them in lots of calculations, and when you say you're doing a calculation at standard temperature and pressure, everyone knows what you're talking about. So standard temperature is 0 degrees Celsius, which is 273 Kelvin. And then standard pressure is 1 atmosphere, which is 760 mmHg. Okay, so you understand these are the same measurement, just in different units. We often abbreviate standard temperature and pressure as STP. And then there's this conversion factor that's really useful to know, and I've seen it show up on the UVU test. At standard temperature and pressure, 1 mole of gas, no matter what gas it is, it could be oxygen, hydrogen, carbon dioxide, whatever it is, if you have 1 mole of it, it is going to fill up 22.4 liters. Okay, and it doesn't matter what the gas is, because remember how last time we made all these assumptions that the volume of the gas doesn't matter and the gases aren't attracted to each other or anything, so we kind of just imagine them as they're all exactly the same and they all take up exactly the same amount of space at standard temperature and pressure. So you can have problems like this one. How many moles are in 50 liters of O2 at STP, at standard temperature and pressure? So this is pretty simple. All you need to do is take 50 liters and then use this conversion factor. So you know 22.4 liters is 1 mole. So 50 liters is going to be like pretty close to 2 moles. I'll get a calculator here. This ends up being liters cross out, of course. We end up doing 50 divided by 22.4. And it gives us 2.23 moles of O2. Okay, pretty simple. So just know STP and be able to convert between moles and liters in STP. All right, so knowing that, we're now going to move on to these gas laws. There's 3 of them. They're named after different people that discovered them. First one is called Boyle's Law. So Boyle's Law says that as the volume of a gas decreases, pressure increases. Okay, so a simpler way to write this could be as volume goes down, pressure goes up. So when you have a relationship where one thing goes down and another thing goes up, that is called an inversely proportional relationship. And that should make sense to you guys. If you imagine compressing a gas, making it take up a smaller and smaller and smaller volume, it should make sense that it gets higher and higher pressure. Okay, so there's actually a mathematical equation for this law. It looks like this: P1 V1 equals P2 V2. So you can probably guess the P and the V stand for volumes. The 1, these are like the initial pressure and volume. So let's say I start with a gas that's like taking up this much space and it's at some pressure. And then let's say I move it to a new volume like this. I could use this equation to calculate the new pressure, which would be higher than the original pressure if I'm decreasing the volume. Okay, and we'll talk about calculations with these in a second. But the next law is called Charles' Law. And Charles' Law says as the temperature of a gas increases, the volume increases. Okay, and that also should just make sense to you. You heat up a gas, it's going to expand. And the equation for this one is a little bit different. It's got a fraction. We've got V1 over V2 equals T1 over T2. Okay, so we can start with our initial volume and our initial temperature and put in our new volume, and we could calculate what our new temperature would be, or vice versa. Okay, just one note, for Boyle's law, this is true if the temperature is constant. For Charles' law, this is true if the pressure is constant. So whatever thing you're not measuring in these has to be constant. We could write this one as temperature goes up, volume also goes up. So these are what we call directly proportional. Temperature and volume increase together. When you increase one, the other one increases as well. Okay, the last one is called Gay-Lussac's law, and it says as the pressure of a gas increases, the temperature increases. And again, this is if you do this at a constant volume. If you can change the volume, then things will be a little bit different. But so pressure and temperature are also directly proportional. And the mathematical equation for this law looks like this. Looks a lot like Charles' law, except with pressure instead of volume. Okay, so basically we have relationships between all these three different things, these pressure, volume, and temperature. And what we can do is we can take these three laws and we can combine them into this thing called the combined gas law. And this is actually going to be the one that you want to remember, that you'll want to write down on your study guide, because it's really helpful and it incorporates all three of these. So you don't really need to know these individually if you know this one. So the combined gas law is like this. P1 V1 over T1 equals P2 V2 over T2. So what you can do is if you have problems like these ones down here that we're going to do, they give you an initial pressure and volume and temperature, and they want you to solve for, say, a new volume, and they give you the new pressure and temperature. You can plug all those things in and solve for x. So you're going to do a little bit of algebra here. One thing to know with this equation, if the problem says that something is held constant, so like something's not changing, then you can just cancel that part of the equation out. So if we have an equation where pressure is held constant, you can just cross out the p's and then just do V1 over T1 equals V2 over T2. And we'll see an example of that too, so don't worry. One thing that's really, really important to remember though, when you do temperature, you have to use Kelvin. You cannot use Celsius. Okay, it will not work if you use Celsius. So always use Kelvin. Generally, it's pretty normal to use ATM for pressure and liters for volume. But as long as your two volumes are the same units, your two pressures are the same units, you should be fine. But you got to use Kelvin for temperature. Okay, so we might have to do some conversions here. Okay, so let's look at this next example. A sample of gas has a volume of 400 liters when its temperature is 20 degrees Celsius and its pressure is 300 millimeters of mercury. What volume will the gas occupy at standard temperature and pressure? Okay, so what's kind of useful before we start plugging stuff into the equation is to figure out what all of these numbers are. So let's just write P1, V1, T1, P2, V2, and T2. Not a lot of space there, that's okay. Okay, so we know it's starting with a volume of 400 liters, so that's our V1. We know it's starting with a temperature of 20 degrees Celsius, but we need to convert that to Kelvin. So we would need to add 273 to that, so that's going to be 293 Kelvin. And then the pressure is 300 mmHg. And I can leave it in mmHg as long as I do my other pressure measurement in mmHg. It's asking me what volume the gas will occupy at standard temperature and pressure. So it's asking me for V2. It's asking me to find that. And it's telling me I'm going to be at standard temperature and pressure. So standard pressure is 760 mmHg. And standard temperature is 273 Kelvin. Okay, so I can go ahead and plug all of this into my equation now. So remember, my equation is P1V1 over T1 equals P2V2 over T2. So I know my P1 is 300 mmHg multiplied by my volume, which is 400 liters, divided by my temperature, which is 293 K. It's going to be equal to my new pressure, which is 760 mmHg. My volume is X, that's what I'm solving for. And then my new temperature is 273 Kelvin. Okay, now all of these units will cancel out except for the volume, which I'm trying to find. So when you have fractions like this, the best way to do it is to multiply the bottom of this fraction by the top of this one, and the bottom of this fraction by the top of this one. I don't know if you remember from math that you can do that, but you can. So I'm going to do 273 times 300 times 400. It's a big number. 3276000. And there's a lot of units on that number. I've got mmHg, liters, and Kelvin. And then on the other side, I'm going to do 293 times 760. And I've got an X over there. So this is 222,680 mmHg and K. And then I've got X. So now I'm just solving for X. So all I have to do is divide by my 22,000. Sorry, I'm running out of space here. mmHg and K. Divide by my 222,680 mmHg and K. So those cross out, those cross out. My numbers look like that. And I end up with X equals 147 liters. Okay, that was a pretty long problem, but let's see if that makes sense. I increased my pressure, so that means my volume should have decreased, which it did. It went down. So this makes sense. Cool. Okay, let's look at another problem. This one says, a sample of gas has a volume of 500 milliliters under a pressure of 500 mmHg. What will be the new volume of the gas if the pressure is reduced to 30 mmHg at constant temperature? So see there where it says constant temperature? That means I can just cross out the temperature part of this equation. I don't even have to worry about it, which makes this way more simple, because then I just have to worry about P1, V1, and P2 and V2. So it tells me the volume is 500 milliliters and the pressure is 500 mmHg. It wants the new volume if the pressure goes down to 300 mmHg. Okay, so now I can just plug everything in. So P1 is 500 mmHg times 500 milliliters equals 300 mmHg times X. Divide by 300 mmHg. I'm being really good about writing my units. I'm not always this good about writing my units when I'm doing algebra, but they do always cancel. It's kind of nice to see. Okay, and then I just multiply these two numbers and divide by 300. Oops. Divided by 300. Okay, hang on. 500 times 500 divided by 300 equals, there we go, 833.33 milliliters would be the answer to this problem. All right, so that's how you do gas loss. Let me know if you have any questions.